Well,
Okay.
good morning or good evening, everyone. This is Bob Gluthero, and I am a product marketing manager in the data portfolio here at Pivotal. And welcome to the community call for MADlib. Today we'll be doing a deep dive into the features of release 1.13. And joining us today we have Jingyi Mei and Nikhil Kek from the software engineering group to walk through the new functionality. So with that, Nikhil, please take it away.
Hello, everyone. My name is Nikhil. I'm a software engineer in the MADlib engineering team. Today, we are going to talk about the new MADlib release V1.13. V1.13. It was released on 22nd December of last year, 2017. Mostly we'll be talking about two main features, but I just wanted to give you a rundown on what happened in this release, and then we can go back to talking about a couple of features. So the biggest feature that we introduced in this release was hits. It's a graph algorithm, which we are going to talk about in more detail in a presentation, so I'll hold off on that for now. There were a few improvements to the KNN function as well, and we are going to give you a small demo of that as well, so I'll not talk about it in detail right now. The other features that we see here is we added grouping support for MLP. So now what you can do is you can pass a grouping column to the MLP function, and it will treat each group as its own entity and do the training there. With cross-validation, we improved the stats reporting. What that means is the output table was a bit ambiguous in what it was reporting, and it was not really clear what the labels were. So we improved that. We added some more examples and user docs about it to make sure that people understand what it was reporting, to be more explicit. Lastly, correlation. There was a feature request that correlation used to ignore null values, but now we don't ignore null value, and instead we replace it with the mean of that tuple. So those are the basic things that we, at least feature-wise, that were introduced. There are a few more bug fixes, but I think we can start diving deep into the hits and the KNN, which were the two major features. Before I go there, does anyone have any questions? Okay, let's move on then. Cool. So hits is a graph algorithm that we introduced. We did not have we had PageRank, which is a similar function, but what hits does, which is called hyperlinked induced topic search. It's a graph link analysis algorithm which was developed by John Kleinberg. The basic use case back then was to rate web pages, and the way it does that is it assigns something called as hub and authority to all the vertices. So that is kind of analogous, like authorities are analogous to web pages that have good authoritative content, that have good quality, and that get linked to by other pages. And on the other end, hubs can be thought of as large directories or repositories which do not have quality content themselves or authoritative content themselves, but they provide links to other authoritative pages. So that's how authorities and hubs are linked to each other. Okay, so you see a graph on the right, which is a very small or basic graph for illustration purposes. And what it shows here is a few vertices who have incoming and outgoing nodes. So the basic idea behind this algorithm is, by the end, when you call hits in MADlib, at the end it assigns hub and authority scores based on the structure of the graph. And then the users can interpret it in any way they want to and take actions based on these scores. All right, so we won't go into the detailed math behind it, but the math is not too difficult. The only thing that we have to figure out is you start with default hub and authority scores for all vertices, which is, well, in MADlib we start out at 1, and then what you do is you sum all the hubs. So for a given vertex, you sum all the hub scores to that vertex and then assign that as authority. And similarly, what you do for hub is you take all the hub score, all the authority scores to that vertex and sum it up, and that's your hub score. And you keep doing it iteratively. And we'll go into more details when we do the demo, when Jingy does the demo. So any questions so far? Okay. So the basic use cases of hits, mainly it was developed for web search to rank web pages essentially, or help with it. But one other use case that is also helpful is the scientific impact of researchers or journals in a way where if two journals are kind of receiving the same citations from different papers, it's sometimes hard to compare about the prominence of that journal. So another way of looking at it is that you need to know where it's getting linked from. If it's getting linked from a page which has high authoritative content, then it gets more points than a journal which has links from a low authoritative content web page. So that's one of the major use cases for hits. Okay. So we thought we had add a small slide for how a graph is represented in MADlib specifically. This is a generic way of representing graph. You see these params. We don't, like, hits does not need all of this, but this is how MADlib represents a graph. So you have two things. You have a vertex table and you have an edge table. The vertex table is really simple. You just have the vertex IDs, which are just the nodes. You see vertex params there, but for our intents and purposes, hits does not use any vertex param, so you can just ignore it. Edge table is also pretty simple. All you have is a source and a destination, so you can know which node has an incoming node, which node has an outgoing node, and then you can have an edge weight as well. There are some edge params as well. For example, you could group each graph, but we will look at that in detail when we look at the demo. Okay. This is the interface for hits. I'll quickly go through it, and then Jingy will give you a rundown of the demo and go through each one of those parameters. The first is the vertex table itself, the name of the vertex table. The second one is the vertex table column, which contains all the vertex IDs so that we can uniquely represent each node or vertex. The third one is the name of the edge table. That's pretty straightforward. The fourth one is edge args. So edge args are, you need to know which your source column is, which one is your destination column, and if you have any weights column. The next one is out table. This is the name of the output table that will contain the results of the hits computations. The next one is max iter. This is how much you want to iterate on, the number of times you want to iterate your algorithm on, and the default is 100, but we'll go through that in a minute. Threshold is whenever you want your algorithm to stop. That's pretty straightforward. And then the grouping columns is if you want to divide your graph into subgraphs depending on the column, then each subgraph will become its own graph and it will have its own hub and authority scores. So that's just the basic interface. Now I will pass it on to Jingy to give you a small demo of it.
Thanks, Nikhil. So let's go to the demo. So hi everyone, I'm Jenny May. I'm also a software engineer from MADlib team. Now I will go through the demo of hits algorithm. So currently this Jupyter notebook is connected with my local Postgres instance. So we can see the MADlib version is 1.13. So we can start create test tables for hits. So firstly, we will create two tables as mentioned before. The first table is called vertex. in which in our case, we only have an ID column, which is a unique identifier of each vertex. The second table we're going to create is an edge table. In our case, we only have two columns here. The first one is a source, and the second column is a destination vertex. So I will insert 7 vertex here into vertex table, and I will insert several edges into the edge table. So in the edge table, you will see like, for example, the first data is like vertex 0 points to vertex 1. So I will create those two tables by running this. So now we got both the vertex and the edge table ready. Next, we can call MADlib hits to calculate hit score. So here is, this is a very basic use case for hits. Let's look at the input. The first one is the vertex table name. In our case, we name it vertex, so I just put vertex here. The second column is the vertex ID column. In our case, we name it ID, so we put ID here. The third input is the edge table. In our case, our edge table is called edge, so it's edge here. The fourth column, which is comma delimited string of edge arguments. So basically, the first one is saying like, in my source, in my edge table, the source column is named what, and the desc column is named what. So in our case, the source column is SRC, and the desc column is DEST. So if you have a customized table with different column name, you can just put the correct column name here. The last parameters I put here is the output table, which will say the output result of the hits. So you basically, as a user, you can name it whatever you want as long as this table does not exist in your database. So in my case, I will just name it hits out. There are more inputs that you can specify, but here for this example, I will just use the default value for them. I would like to explain more. So what got ignored here is the max iteration. So here, the max iteration is 100, which means this model will run maximum 100 times and then stop. The other one I ignored is the default threshold. In our model, we just calculate as 1 divide the number of vertices in the table multiply 1,000. The last one is a group column. So in this case, I don't have any group by column, so I just skip that. So let's run this and select everything from the hits out table. So in this table, we will see the authority and hop score are ordered by the vertex ID. So I will see for every vertex, it will have authority and hop score. And also because we do normalizations for both authority and hop, so all the values of authority and hop are between 0 and 1. Besides this hits out table, we also create another table with a suffix underscore summary. So in our case, we have a table called hits out summary. This table, if I select from this table, we will see iteration number is 17, which means for our data, this module runs 17 times to converge and stop calculate. So we can also customize our module by put more parameters. This example shows the user can specify the max iteration number. So different from the above example, I specify 3 here, which means I only want this module to run 3 times. So if I run this, I will get a new hits out table. If we compare from the previous round, the score for every vertex is slightly different. And if we select from the summary table, we'll see this module only runs 3 times and then stop. Additionally, we can also tune another parameter, which is called threshold. So in this case, I will say make max iteration as null and make the threshold at 0.5. So the definition of the threshold here is the difference of the authority and the hop score from the current run minus the previous one. So I will say I will calculate the difference after. So for this iteration, I got the score for authority, and then I will use this authority score minus the previous authority score and say if the difference is under this threshold. Also, same thing happens to hop. So as long as both of the difference is under this threshold, the module will stop running. So in this case, let's run this and we will get a new hits out table. And if we look at the iteration number, we'll see this module only runs 2 times because 0.5 is kind of a big amount here since every score is between 0 and 1. So this module converged very quickly by just 2 runs. Besides, we can also use a combination of max iteration and threshold. So in this case, we set max iteration as 20 times, and we set the threshold as 0.00001. In this case, the module will stop by whichever criterion meet first. So if 20 times reaches first, it will stop. Otherwise, it will keep calculating until it reaches the threshold. So if we run this, we will get the hits out table. And if we look at the summary, for this specific case, it keeps running till the 20 times max iteration reaches. So those are different use cases for the case that we don't use grouping, and we actually have support grouping. So for grouping, that says you can actually make your edge table into different groups. So I will recreate the vertex table and edge table. For example, I will insert the same vertex ID, but for the edges, I will have 2 groups. If you look at the third column, the first part, they all belong to user ID 1. The rest of them, they all belong to user ID 2. So in this case, I want to calculate the authority and hop score for different groups. So actually, they are 2 graphs, and they will be calculated separately. So I will recreate those 2 tables and run the module with all default input parameters, and I will specify user ID as a group column. So if I run this, I will get a longer output table, which lists, say, for user ID 1, vertex ID 0 to 6. What is their authority and hop scores? And for user ID 2, from vertex 0 to 6, what are their authority and hop scores? Similarly, we will have a summary table for this because, as I mentioned before, it calculates the authority and hop scores separately for user ID 1 and user ID 2. So here we will say 2 groups here. So we will say for user ID 1, the module runs 17 times to converge, and for user ID 2, they run 16 times to converge, which means even if the user ID 2 converged, the module will keep calculating until user ID 1 also converged. Those are main use cases for hits, and there's there are some specific corner cases we want to cover here. Say in a graph, sometimes for a specific vertex, there might be no incoming edges or no outgoing edges. So if you think about it from the definition of authority and hop score, for a vertex, if it doesn't have an outgoing edges, it doesn't work as a hop. So the hop score for that should be 0. And the other way, for a vertex, if there's no incoming edge, means it doesn't work as an authority because no one else refers to it. So it will have a 0 score for authority. So in this case, we will create the vertex and edge tables specially. So we will see in the edge table for vertex 0, there's only outgoing edges but no incoming edges. And for vertex 3, there's no outgoing edges but incoming edges. So I will create the table and run hits again. So here we use 100 as the default max iteration, and we will get the result table here. So in the table, we can say for vertex 0, the authority score is 0, and for vertex 3, the hop score is 0. This is a edge case we want to cover. So basically, those are all examples we want to demo for hits. Any questions for the examples? Okay. The last thing about hits is that we want to mention the performance of hits algorithm on Greenplum. So we did experimentation on a Greenplum cluster with one master and 4 segment hosts. So in this in this graph, the number of vertices is 1 million, and we increase the number of edges. So we can see the performance of hits. It keeps in a pretty linear performance as the number of edges increased. So that's what we want to cover for this new feature for hits. Is there any questions? Okay, then we will go to part 2. We will cover some improvement we did on k-nearest neighbors. So we implemented k-nearest neighbors earlier before. And this time for release 1.13, we added, basically we added 2 more columns that we want to highlight here. The first column we want to highlight here is the output neighbors. So previously in the output table of KNN, you cannot see what's exactly the neighbors. And here we add this new column. So if you make this column as true in your KNN output table, you will see the exact list of the neighbors of the current node in the training set. And the second parameters we add is this function. So in this case, we support a customization of the distance you want to use to calculate the distance between 2 nodes. So we provide the following different distance functions. For example, we support norm1, norm2, square this norm2, this angle, and this tanimoto. And what we want to also mention is we actually support a UDF. So if you have other requirements, if you want to define your specific calculation for distance, you can actually define it and specify it in this parameter. So the signature required for the user-defined function is we only the input is two input with a double precision, and the output is also a double precision. So we will run some example to show how the module looks like. I will firstly load the data for KNN. So this training data is simple. I have an ID column as a unique identifier. I have the actual data for each node, and I have a label as a third column. So I will load the data first. And also I have another table as a test data without label, which is similar as the first one, but without label. So I will load the test data. So now I will run KNN for classification. So here, all those inputs are as same as before. And here you will see we make this column as true, which is the new column we introduced. Which means in the output table, it will list the neighbors in the list. And also for the distance function, I specify it as square this norm 2, which is already built in MADlib schema. So I will run KNN in this way and look at the output table. Here we will see the last column in the output table. It will have a list of the k nearest neighbors. So in our module, because we specify k as 3, so for every testing data, we will say 3 neighbors for it. And also this module the distance is calculated by square this norm 2. There is another use case that we want to cover is sometimes for data scientists, they don't really want to do prediction. They just want to calculate the k nearest neighbor for a specific node. So if you want to do that, there is a way that you can specify now here in the training labels column, and you can either specify true to list the neighbors. Even if you don't specify true here, if you make the label now, MADlib knows you're not going to do the prediction, and it will give you the neighbors. And also you can specify whatever kind of norm distance you want to use. So if I run this module, I will say in the result table, there's no prediction column, but there's a k nearest neighbors column. So for each test data node, I will say what's the actual data it has and what's the k nearest neighbors for it. That's the cases we want to cover for KNN improvement. Any questions for this? So I think that's pretty much of what we want to introduce for 1.13 today.
One other thing, the KNN module was developed by a developer from outside the MADlib engineering team. So just wanted to mention that.
Okay, great. Yeah.
That's great. Thank you. Hi, this is Rashmi. I just had a quick question. With the both these new algorithms, sort of, were they requested on the by users, or were they just next on the list of very important things or rather the hits one was new? This is an improvement, right, KNN?
Yeah, it's Frank speaking. With the hits, that one was requested by a customer we work with who does graph processing. So hits was a component of a security analytics use case that they were working on. On the KNN side, The KNN algorithm that's kind of in development now. It's sort of in the second or third phase. And one of the things we knew we wanted to add was the user-defined distance, because that's something that we have in other MADlib modules. I'm thinking, for example, of clustering with k-means. So it seemed like that wasn't specifically asked for, but it seemed like a logical thing to add for our users to pick a distance function of interest or define a UDF of their own for that distance function.
Okay, great. What is the next release going to be more about 2.0 or is there a 1.14 coming up?
So the way the JIRAs are set up now is there is a 1.14 planned. And the 1.14, there's a bunch of different themes for it. It continues along the graph kind of path. So there's a couple of new graph algorithms. There's JIRAs for those. I know that there's a JIRA, there's a pull request out there for a sampling algorithm for balancing data sets in the case that you want to do some kind of balancing before you input to predictive algorithms. And then there's a bunch of other things. One that comes to mind is supporting newer modern versions of GCC, the C compiler. So there's work being done now to support that. But if anybody has any ideas or would like to work on any of these JIRAs, then they're from the community, they're more than welcome to contribute.
Great, thank you. That sounds good. The balancing data sets will be very useful. It's quite a common ask.
Great, thank you.
Okay, this is what we wanted to give you a demo of for KNN and HITS. If we don't have any more questions, I think we can wrap this up.
Okay, well, thank you for attending the call, everyone. And as always, a recording of this will be put up on the YouTube channel very shortly, so look for that later today.
Thanks, Bob.
Thanks a lot.
Thank you, everyone, and have a great day.
Thank you. Great work.
Bye.
Bye.